Concurrency is a type of execution where the different parts of a program can run independently of each other. In other words, the task can be executed out of order so that each part of the program can exchange information from each other or write information to each other. In combinational logic circuit, the output is a function of the present inputs. The assign keyword is used to designate a logical expression to an output. This kind of assignment, a net means a variable that has been declared as either a wire or a register. Always is a keyword used to implement an always block. If your always block contains one statement, then you don't have to enclose your block with a begin and end keywords. An always block will always execute the statements inside it. Therefore, you need a trigger to prevent it from executing infinite times. So unlike the initial block which executes only once for the entire simulation, the always block always execute. If you don't have an event trigger, or if you don't put a delay, always block execute infinite times. So in this example, whatever you put inside this parenthesis that is labeled as event, that would be your trigger. For example, this always block has some sensitivity for inputs A underscore in, B underscore in, C underscore in, and the same is true for this second always block. When any of these inputs changes its values, always block 0, 1 and always block 0, 2 will execute at the same time. This @ symbol here means that the block will execute at the condition inside this parenthesis. If this sensitivity list is empty or it is missing, then the designer must introduce some form of delay to prevent the always block from executing infinite times. Since Verilog HDL has some similarities with C language, its operator symbols are similar to that of the C language. This symbol plus is for binary addition, and it is obviously used to carry out the addition of two binary operands. This symbol dash is for binary minus, and it is used to carry out the subtraction of two binary operands. This symbol asterisk is for multiplication, and it is used to carry out the multiplication of two binary operands. This symbol / is for division, and it is used to carry out the division of two binary operands. And this symbol % is for modulus, and it is used to find the modulus that is a result from the division of two operands. If you want to process a logical operation, or if you want to feed logic 0 or logic 1 to a logic gate, we use the following logical operators. This symbol $& is for logical AND, and it is used to carry out the logical AND on two binary operands. This symbol, two vertical lines, is for logical OR, and it is used to perform logical OR on two binary operands. And finally, this symbol exclamation point is for logical negation, and this is used to carry out the logical negation for any given binary number. If you want to evaluate two operands in such a way it will return a 1 for true or 0 for false, you use the following operators. This symbol designated by two equal sign is for logical equality, and it is used to compare two operands. This symbol, an exclamation point and an equal sign, is for logical inequality, and it is used to find the inequality for two operands. We have this symbol exclamation point, and it is used to perform logical negation for a given binary number. If you want to perform bitwise operations, we use the following operators. This symbol ampersand is for bitwise AND. This symbol vertical line is for bitwise OR. This symbol is for bitwise XOR. And finally, this symbol is for bitwise equivalence. The following operators are used to compare two numbers, and they return a logic 1 when the comparison is true and logic 0 when the comparison is false. The Verilog shift operators are used to shift data in a bit array. The shift operator must always have two operands. The left-hand side of the operator contains the variable to shift, and the right-hand side of the operator contains the number of shifts to perform. When shifting the values using these operators, the empty bits are padded or filled with zeros. The grave accent timescale is a compiler directive that specifies the unit of measurement for time and the amount of delay. Its basic syntax is grave accent timescale, then you specify the unit, then / precision. Here are the following character string in order to indicate the unit of measurement. For example, S is for seconds, MS for milliseconds, US for microseconds, NS for nanoseconds, PS for picoseconds, and FS for femtoseconds. For example, I want to specify the unit of measurement as 1 nanosecond, so I'm going to type in 1, then NS for nanosecond, then / to specify the precision. In other words, if I specify 1 picosecond, that means if you have a timing diagram, it will round off the scale to 1 picosecond or the value to a picosecond. Next, the changes in value of a variable can be used to trigger the execution of a statement. For example, when a positive edge is detected on this clock variable, this will trigger this always block statements to execute. By the way, posedge means the system detects a transition from 0 to 1 or 0 to x. X means don't care, or 0 to z. Z means high impedance. And also, negedge means transition from 1 to 0 or 1 to a don't care. Negedge can also mean a transition from 1 to a high impedance. This symbol is used to create a blocking assignment. See this example here. And this symbol is used to create a non-blocking assignment. So see this example here. Blocking assignments executes in series because one statement blocks the execution of the next statement until it completes. For example, when you assign 1 to A, this statement must finish executing first before this second statement commences. On the other hand, non-blocking assignment executes in parallel because assignments here can occur at the same time. Ideally, non-blocking assignment is good for sequential logic circuits with feedback coming from the output. By the way, when we say continuous assignment, this means that we are assigning values to nets like a wire. And when we say procedural assignment, this means that we are assigning values to variables. Forever is a keyword used to continuously execute a statement. Later, we will use this to execute clock pulses. $finish is a system task that exits the simulation and returns the control back to the operating system. On the other hand, $stop is a system task used to temporarily suspend the simulation. So later, we will use this $finish to forcibly terminate our forever loop later in our demonstration. Now, from our previous discussion, we use gate level modeling to construct a Verilog code for a half adder. This kind of modeling is easy to implement when the design requires few number of gates and wires. But if the number of gates and their connections increases, sometimes it is easier to code the circuit using other modeling style. So for example, this circuit just contains 4 gates, hence we can use gate level modeling style. But look at these feedbacks. When instantiating each of these gates, the designer may instantiate these 2 NAND gates first before these NOR gates. Or the designer may instantiate these upper gates before the lower gates, and so on. And this difference may affect the operation of these feedback wires. Therefore, in some cases, even if we can use gate leveling modeling style for this flip-flop, it seems that the DataFlow model is easier to implement because we can simply use blocking or non-blocking statements to control the flow of signals. Let's try to code this SR flip-flop using Verilog DataFlow modeling. I'm going to put this here, and this is the table describing the behavior of our SR flip-flop, which we derived from the lecture. Please see the link below to see the recorded lecture where we derived this table describing the behavior of SR flip-flop. To start our coding, fire up your Visual Studio Code, then click File, then New File. So it will ask you to select a language. I'm going to click this link, select a language, and then scroll down, then choose Verilog. I'm just going to write a comment here to describe the purpose of this code. So this is the Verilog DataFlow modeling of SR FlipFlop. We will name this file as, for example, SR FlipFlop. So this would be our module for SR FlipFlop. So click Ctrl S, and let's name this file as SR underscore FlipFlop.v, then save. So I'm just going to modify the timescale by typing grave accent timescale. I like my timescale to be in 1 nanosecond, so I'm going to type 1 ns. Then the precision is also in 1 nanoseconds. So the division of my timing diagram will also be in nanoseconds. I'll type in module space SR underscore FlipFlop. Then its inputs. The inputs of SR FlipFlop is the set signal, reset signal, the clock, and its outputs are Q, and its inverted output is Q bar, which we will just name as QB to differentiate it from Q. S for set, R for reset, and CLK for the clock input. And for the outputs, I'll just indicate it with Q and QB for Q bar. Then I'll terminate this with semicolon. To improve readability, I'm going to indent the declaration. Input. So I'm going to declare SRCLK as inputs. Then I'm going to declare Q and QB as outputs. Before I begin coding the always block, let me point out that later we will be saving some values inside this output variables. But initially, this is currently declared as wire. And we know that wire cannot store binary elements like 0 and 1. Hence, we need to declare this also as registers. So that later, in the simulation, they can store binary elements like 0, 1, or don't care, or high impedance. We will now begin coding this table. In DataFlow modeling, we will not be focusing on gates and their connection, but rather, we will just focus on how these binary elements worked out using this table as a guide. I'm going to write an always block, which will be triggered when I detect a positive edge coming from our input clock. So again, when this always block detects a positive edge coming from our input clock, it will execute the statement inside this begin and end keyword. So for the first case, when, based on this table, when S is equal to 1 and R is equal to 0, the output Q must be set to 1 and the inverted input must be set to 0. To represent this behavior, I'm going to use an if statement. So if set is equal to 1 and R is equal to 1, so I'm going to write, if I only have one statement like Q assigned with the value of 1, then I don't need to enclose this with begin and end statement. But since I will be using multiple statements, I have to enclose this with begin and end statements as well. So to increase readability, I'm just going to indent this begin and end keyword. At this instance, I'm going to equate based on this table. I'm going to assign the output Q with logic 1. And of course, Q bar with the complement of Q. The next statement is set equals 1 and reset equals 1, but this is an invalid input, so we will not be dealing with this. Since we will not be dealing with set equals 1 and reset equals 1, when our code encounters this case, they will just ignore this case and there will be no changes in this outputs Q and QB. By the way, this is 0 based on this table. Next case is when set equals 0 and reset equals 1, then the output Q will be reset to 0. So we represent this in the code as else if set is equal to 0 and reset is equal to 1, then the output Q will be assigned with the value of 0, and we assign the value Q bar with the complement of Q. So for the next case, we have set equals 1 and reset equals 1. So we will ignore this case. And next is set is equal to 0 and reset is equal to 0. And based on our table, when this happens, we will not change the value of Q and Q bar. In other words, the value of Q and Q bar remains the same. Let's type else if S is equal to 0 and R is equal to 0, then we will just retain the value of the output Q and we will retain the value of Q bar, or we could just negate or complement Q. And then I'm going to end this module and Control S to save this module. Okay, let me just correct this data flow. I'll put a W here. So to test this module, this SR FlipFlop module, let's create a test bench. So I'm going to click File, New File, and then click this Select a Language. Scroll down to look for Verilog. Choose Verilog. Let me put a comment here to describe the purpose of this code, though this is not necessary. Let us just name this file as srflipflop underscore tb for test bench. Control S. I'll copy this. And click Control S. Then just paste the file name. Then click Save. Remember this location. So as much as possible, the test bench and the module to be tested are in the same location in case the compiler directive include fails. I'm going to write the compiler directive, grave accent include, then the name of the module. So in case this statement fails, this test bench will be able to access this file if the test bench and the module to be tested are in the same location. So next, I'm going to begin writing the code for this test bench, SR. We don't need to pass any arguments to this test bench, so the port list will be empty. So I'm going to write semicolon here, and then I'm going to declare our inputs for set as S underscore in, though I could just simply write S. Also R underscore in. And the clock as clock input or clock underscore in. Next, I'm going to declare the outputs as wire space Q underscore out and Q bar underscore out. So let's instantiate the module. The name of our module is SR underscore flip flop. So for this instance, let's just name it with SR flip flop 1. Since we only need one instance of this module to test the behavior of the outputs as a function of its inputs. So we will be connecting these input ports and output ports inside this instance. Note that the arrangement is important here. So if you forgot, you have to return to this module about the arrangement of the inputs and outputs, because sometimes you only have one input or sometimes you have two inputs and so on. I'm going to type enter so that I can maximize the space of this editor. So this is valid as long as I do not terminate this list of port list with a semicolon. I can now terminate this with semicolon because I'm done declaring all the inputs and output ports. So before we vary the values of the inputs, let's create some clock pulses. So I'm going to use an initial block here, enter, and then initially the value of the clock input is logic high. And then I'm going to use the forever keyword to change the values of this clock input in an infinite loop. But I'm going to put a 1 nanosecond delay every time I change the value of the clock input. So I'm just going to negate or complement the value of the clock input. So now, I have an infinite loop where I continuously change the value of the clock from 0 to 1 and 1 to 0. So later, you must find a way to terminate this, otherwise, this will execute forever. So later, I'll show you how. Next, I'll begin changing the values of the set input, reset input. So I'll only need an initial block to change the values of the inputs. For the first case in this table, the set signal is assigned with a value of 1 and the reset signal is assigned with a value of 0. So again, our first case is set is equal to 1 and reset is equal to 0. The second case is both of them are in logic 1. Next case is set is equal to 0 and reset is equal to 1. Next is both of them are equal to 1 and then both of them are equal to 0. To clearly see the behavior of these changes, I'm going to introduce some delays between these changes. Let's just introduce a delay of 10 units of time, which in our case, it's in nanoseconds. So this means 10 nanoseconds. So after 10 nanoseconds, we will change its value again, and so on. Now recall that because of this forever keyword, this statement will execute forever. We need to find a way to terminate this simulation, and to do this, I'm going to put a compiler directive here to stop or exit the simulation, and I'm going to write the keyword $finish, then semicolon. Next, I'm going to end this entire initial block with an end statement, and I'm going to end the entire module. Obviously, there will be a corresponding changes in the output Q out and QB out. And to save this, we will dump this to a file. So let me type $dump file. Let's name the dump file with sr underscore FlipFlop.bcd or value change dump. And let's set its setting to 0, and the top module would be this test bench. Then end this with a semicolon. So Control S and click this toggle panel to view the PowerShell and go to the current location of this test bench and the module to be tested. In my case, it's in this location. So I'm going to type cd to change directory and then the location of this test bench. Hit enter. Then I'm going to type clear to clear this terminal. Let's now compile our test bench. So I'm going to type iverilog space -o, and the name of the compiled file will be sr underscore flipflop Of course, you could write a different file name. It's up to you. Underscore tb dot vvp space. The name of our source file is sr underscore flipflop dot v. Click enter. Next, we will run the simulation so that in our simulation, it will produce a dump file VCD. So I'm going to type VVP, and the compiled file is sr underscore flipflop underscore tb dot vvp. So once I execute this command, it will generate this .vcd file or the dump file. So click enter. Next, let's open GTK Wave to view the timing diagram produced by this test bench. GTK Wave. And then click File, Open New tab. Here, I'm going to select, oh, where's the dump file? Okay, the reason why I was not able to generate a dump file is because I compiled the wrong module. I'm supposed to compile the test bench. So I'm going to repeat this again. And here, the source file is supposed to be the test bench, which is sr underscore flipflop underscore tb. So let me enter this. Next, I'm going to run the compiled file vvp sr underscore flipflop underscore tb dot vvp. Now I can run GTK Wave. Click Open New tab. And then choose this dump file. And then click OK. And then choose sr flipflop underscore tb. Choose our test bench. And click any of this signal and then click Ctrl A to choose all of it and then click Append. Recall in our simulation that before the 10 nanosecond mark, we assign set signal with 1 and reset signal with 0. And when I click on this timing diagram between 0 and 10 nanoseconds, note that the set input signal is equal to 1 and the reset input signal is equal to 0. And what we're expecting is that Q will be equal to 1 and Q bar is equal to 0. And based on this timing diagram, our module for SR flip-flop is correct. Next, we assign set with 1 and reset with 1. So I'm going to click on this timing diagram between 10 nanosecond and 20 nanosecond. And note that based on our design, we will just ignore this kind of inputs because these are invalid inputs. So we will not be changing the values of Q and QB. Next case is that set signal is equal to 0 and reset signal is equal to 1. And we are expecting that Q will be set to 0 for this case. So when I click between 20 nanoseconds and 30 nanoseconds, I have a consistent output for Q and output for Q bar. Next case is, again, these are invalid inputs, so we will not be changing the values of Q and Q bar. So if I click on this timing diagram between 30 nanoseconds and 40 nanoseconds, note that the inputs for set and reset are both equal to 1. We did not change the value of Q and Q bar. Finally, if the set signal and reset signal are both in logic 0, we're expecting that there will be no changes in the value of Q and QB. And currently, the value of Q and QB are 0 and 1 respectively. So I'm going to click on this timing diagram between 40 nanoseconds and 50 nanoseconds. I have set signal equal to 0 and reset signal equal to 0. And note that my outputs Q and QB remains the same. Therefore, our module for this SR flip-flop using the DataFlow modeling is consistent with our table that describes the behavior of our SR flip-flop. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!